All right, thank you. Yeah, about a half a year ago, Richard Tilly approached me asking whether we should organize a hot topics workshop on perfectoid spaces. And well, I'm always glad to be at the MSRI, so of course I said yes. But, I mean, I'm very glad that we got this tremendous list of speakers, and I'm very glad they all accepted to speak. I think we have some very good speakers here. And I mean, I'm extremely surprised by the sheer number of people coming. So, yeah, but it's great that you're all here. So I want to give a general overview talk. And I mean, I'm going to say many things which will probably be not so clear when I say them now, but I hope that the other talks in this conference will help to. Also, I want to give an overview of everything that will happen this week. So for me, everything, my work on perfectoid spaces got started with a suggestion that Rappaport gave me. So Rappaport suggested that it should be possible to reduce what's called the weight monogamy conjecture to equal characteristics after some highly ramified base change. So let me just very briefly say what this weight monogamy conjecture is. So that's a conjecture made by Deligne in around 1970 in some form. And so it says the following, that if you have some proper smooth variety over the p-adic numbers, and you pick any integer, any cohomological degree I, then, and I guess also any prime different from p, then on the état cohomology group of this guy which has some Galois action, there are two natural filtrations called the weight and the monogamy filtration, and the conjecture is that the two agree. So I won't make it more precise than that for now. So in Anna Karajan's talk, I think she will speak about it and say precisely what the conjecture is. What matters to us now is that Deligne, in his Whale 2 paper, which was in 1980, proved that the analog is true over an equal characteristic field. I should also probably say that this weight monogamy conjecture is probably the most important open conjecture, or one of the most important open conjectures on the état cohomology of algebraic varieties. So there's some real interest in proving this, and so over equal characteristics, this was known since the 80s, but it's somehow impossible to do Deligne's argument over the p-adic field, because it's using properties of L functions which are known somehow over a function field and characteristic p, but L functions for varieties over number fields are, of course, an extremely hard object. And so one way to interpret this highly ramified base change is to try to use an astonishing theorem of Fontaine and Vinton-Berger. Which, I didn't look it up, I think it's somewhere from the 60s already. Is that right? I would say 70s. Okay, 70s. So I guess it didn't exactly consider this field, but anyway. So you can consider the field where you adjoin to QP many p power roots of p, so or all p power roots of p. So this gives you an infinitely ramified extension. So infinitely ramified over. Ramified over QP. And then there's this very surprising result that then the absolute Gower group of this Laurent series field is isomorphic to the absolute Gower group of K, which of course is a subgroup of the absolute Gower group of QP. So in other words, after you make this infinitely ramified extension, the series of finite extensions of those two fields are exactly the same. And so one could then ask the following question. So given some x over k, can one relate, or can one realize the Galois representation, which is a cohomology, the LRA cohomology of this variety in characteristic 0 as the cohomology of some other guy x prime for some other variety x prime which lives over this long series field, and such that this identification is somewhat compatible with the Galois action. If this was possible, then one could use Deline's result to get the result in characteristic 0. So in other words, the question is whether does some of the relation between this field K and this eco-characteristic field extend to higher dimensional objects. So x somewhat corresponding to some x prime. And it was somehow in this mindset that I found this notion of perfectoid spaces, and this let's call this so phase 1 of perfectoid spaces. Because during the workshop we will see many different applications of perfectoid spaces, and they are used in very different ways. And for this reason, I want to distinguish between different phases of the theory. So so the example that I tried to understand was whether there is a relation between the projective space over this characteristic zero field and the Pn over this eco-characteristic Laurent series field. Because obviously some of Pn should correspond to Pn, whatever. I mean, you can't have any other chance if there is such a theory somehow. But there's one important difference. Namely, in characteristic P, you have the Frobenius. So, more generally, we can consider the Frobenius on Pn over any field, which is just on our coordinates given by raising to the P's power. So, in characteristic P, that would be the Frobenius, and characteristic 0, well, it's not, but it's somewhat similar. So in characteristic P, phi is a homeomorphism of the underlying topological space. So in particular, a bijection on points, and it's also a homeomorphism for the état side. So somehow all the topological information in characteristic P for all the topological information, the Frobenius doesn't do anything. But the same is not true in characteristic 0. And it turns out that to get this comparison, you somehow have to make Frobenius a bijection. So also we can look at this case there. So there we had to adjoin all the p-power roots of P. And so somehow we had to adjoin lots of p-power roots. And so some of the same happens here. Also the same here. So one can ask the following more refined question. Is there a relation between the inverse limit over Frobenius in characteristic 0 and the inverse limit over Frobenius in characteristic P, where some of the characteristic P guy doesn't really change much under doing this. So you can also regard this as just the Pn. And the answer that we will elaborate today and tomorrow probably is that there is that the answer is yes. So in a suitable setup, the underlying topological space is isomorphic to the underlying topological space of Pn and equal characteristic, and also the same with état sides. And I should mention that at the time that I thought about these things, I was, on the one hand, very much influenced by some periodic Hodge theory and relative setup, so with some base, where there is some comparison between categories of finite detail covers in characteristic 0 and characteristic P through what's called the Founting's almost purity theorem. And on the other hand, there was a paper by Kit Laya called Non-Archimedean Geometry of Witt Vectors, where he proved something very close to this fact about topological spaces. And so, yeah. So, okay, so. But at the moment, this is something that only works for projective space. And well, for projective space, the weight monodromy conjecture is trivial anyway, so we want something more refined. So I should say, so we want more examples. And so one way to produce examples is the following. So in characteristic 0, start with any what one might call the dynamical system in some sense. So consisting of some variety x and a Frobenius phi. So x is some variety over k, and phi is a lift of Frobenius. Meaning that there is implicitly some integral model for x, and phi lifts the Frobenius of this integral model. P. And then one can show that in this case there will exist some x prime over the Laurent series field such that the inverse limit over Frobenius of x corresponds to x prime in some sense. Generalizing the situation which we had for projective space. So this gives one more examples. One could take for x the canonical lift, say, of some ordinary elliptic curve, or maybe also an NBM variety. And for phi is a canonical lift of Frobenius. So, well, the slight generalization of the case of projective space actually allows you to handle some more interesting varieties. So this phi also, by the way, has a nice property that it's not only finite, but also étale in characteristic 0. Which is not the case for projective space with this phi, which is somehow ramified at the boundary. So you can also cook up some examples where this phi is étale. So the diagram is that what we're interested in are varieties over k. And really we want to get to varieties over this Laurent series field. But you can't compare them directly, but there is this category of perfectoid spaces. Over either field. And these perfectoid spaces, they are just literally equivalent over both fields. So making something perfectoid somehow corresponds to taking this inverse limit over Frobenius. And after you've done that, the categories are just literally equivalent. And it preserves all information you would like, so the topological space, the étale site, etc. And in characteristic P, there's a functor, which I guess I call these guys x prime, sends x prime to the inverse limit over Frobenius of x prime. And really of the associated rigid analytic variety, probably. But there is no such functor in characteristic 0. But what you can do is you can somehow enrich a variety to such a pair x phi. And after you've chosen such a lift of Frobenius, you can then again do the same construction of sending x to the inverse limit over Frobenius. But there's no canonical way of going from a variety to a perfectoid space. And probably already gives this equivalence here a name, so I call this a tilting equivalence. And maybe I've given some idea of why I call this tilting. So usually you would think of the ZP direction as being somehow orthogonal to the FP direction. So thinking of the total space maybe as some ZP power series T. And then you're starting with something over here. So that's the x, and then you tilt, and then you get the x prime here. Okay. However, most varieties X do not admit a lift of Frobenius. So I've just told you that P1, of course, admit was 1, and elliptic curves admit 1. So I talked only about ordinary ones, but if you work a little harder, you can also consider general ones. But curves of genus at least 2 do not. And so it's somehow not clear how to use the theory to say anything about them. But one can do the following differencing. Which works to some extent. So, of course, you can take any x, which I will call also x0, and embed it just into projective space over K. In any way you like. And then you can look at the following tower. So this variety we're interested in embeds into Pn. And then on Pn we have this, we know what to do to pass into this perfectoid world. We can just look at this tower of Pn's connected via the Frobenius map. And of course, you can just pull back this tower and get some tower of varieties over K. And then it turns out that the inverse limit of the xi's, which is contained in this inverse limit of Pn's is a perfectoid space. So you can always cover any chosen variety with something perfectoid by going up one such tower. However, it does not tilt to an algebraic variety. So let me give an example for this. Let's start with something very simple. So just a line in P2. So x0 plus x1 plus x2 is equal to 0. And P2 over K. Then if you do this Frobenius pullback, the xn's will be given by Fermat curves where these exponents are getting bigger and bigger. So there are Fermat curves whose genus tends to infinity. And just topologically, you can regard the inverse limit of the xn's as a subspace of the projective space over this Laurent series field. But it will look like really strange. So it will not be given by algebraic equations, but it will look like something like this. So if you intersect it with a line, then it will meet this line in infinitely many points. So it's somehow a curve of infinite degree, and well, some kind of really weird object. So maybe a good way to think about this is that there's some kind of fractal corresponding in some sense to the dynamical system. Of P2 with this phi. But then there is one lemma which helps you in some cases, namely that if x in Pn is a complete intersection, then the fractal can be approximated by algebraic varieties. Meaning that in any small open neighborhood of this fractal, you will be able to find algebraic varieties of the correct dimension. So in this case, there are some curves which follow this fractal very, very closely. And well, the way to prove this is just to take the defining equations for this complete intersection and then approximate them by some algebraic equations on the other side. Unfortunately, this works only for complete intersections. And one might hope that the lemma is true in general, but I couldn't find a way to prove it. And in any case, using this lemma, you can then relate the cohomology of this x you're actually interested in with the cohomology of these algebraic varieties and equal characteristics. So this way you get the Wakeman-Monogamy conjecture for complete intersections. So not being able to somehow get rid of this this restriction to complete intersections there, I got back to applications to Pierre-de-Koch theory, which is in some sense also where this theory most naturally belongs. So as I said, this was all motivated by, so all the ideas were motivated by previous work in Pierre-de-Koch theory, so Faltings, Gelaya, and also the Falk-Fontaine theory of the curve had some influence on my thoughts. So the basic idea that's somehow pervasive in Pierre-de-Koch theory, so at least since the paper of Faltings in 1990, probably earlier than that, is to, well, at least in this language, is to cover varieties, at least locally, by perfectoid spaces. So the idea is that you have some x again over qp maybe, and you analyze this by considering opens inside of U, and then taking some large cover, so as we did, so some profinite état cover, such that this guy U tilde would be perfectoid. Yeah, I mean, I do everything really in the rigid analytic world. So really everything that I said should be interpreted in some version of p-adic analytic geometry. So say as a rigid analytic variety. But I mean, we will introduce today and tomorrow the theory of adic spaces, which is one way to make sense of rigid analytic geometry for things which are not of finite type, such as these perfectoid spaces, which correspond to highly non-Euclidean rings. So, for example, what you might do is you take Pn, and inside there you take the torus gm to the n, and then over it consider gm tilde, which is inverse limit over this same phi as always. And some, and this cover, so extracting p-power roots of units, this was used in Pierre-de-Koch theory for a very long time, this construction. So I should say that one can tilt U tilde to some perfectoid space in equicharacteristic. And you might hope that some of these U tildes, they come with some transition maps, and you might hope that you might patch them together again to some algebraic variety in equicharacteristic, but that's not what happens. So some of this tilting is something that's totally not important, so forget about tilting. So you might think that, well, perfectoid spaces are only good for tilting, but that's that's not the truth. So they have some other very special properties which help you in the setup. So what are these properties? So the key property is that they are very small FP étale cohomology. So it occurs only in degree 0 and 1 for affinoid varieties. And there's even a better statement. So they're in some sense almost contractible, meaning higher cohomology groups vanish, which is really the content of the almost purity theorem in some sense. So there is the almost purity theorem, which was a key technical ingredient of Faltings's approach to Pierre-de-Koch theory. Which is the approach I'm following here. And in Faltings's work, the almost purity theorem had some very difficult proof and was only proved under certain technical hypotheses related to some kind of semi-stable reduction. And it turned out that the theory of perfectoid spaces allows you to prove a very general form of the almost purity theorem. And it's somehow just this almost purity theorem which you really use in this application of perfectoid spaces in Pierre-de-Koch theory. However, to give you some flavor of, so there are certain new phenomena that occur once you pass to such large perfectoid covers. And I just wanted to give you one example of such a new phenomenon that occurs here. So I apologize for the terminology, but I think it's in some sense a good way to think about it. So one can make sense of what might be called differentials of R over the field with one element in this setup. So what should this be? So Z over F1 should have dimension 1. And I guess it should also be smooth in whatever sense. So you would expect that differentials of Z over F1 are a free Z module of rank 1. And so we should have an exact sequence where in the interior you have these differentials of R over F1 which project to classical differentials. And the kernel should be omega 1 of R of C over F1 tends it up to R, which of course should just be isomorphic to R. any rings for the moment, yes. I say what I want. So let now R be a smooth QP Tate algebra. So as in Tate's original paper on rigid analytic geometry. So it's a Banach algebra which is topologically finitely generated. And which is smooth in the relevant sense. So, okay. So the proposition is that, which I guess it's called Falting's extension. For any perfectoid R algebra R tilde, there exists some object that one might term the differentials of R over F1 base change to R tilde. So this is compatible with base change in R tilde in the expected way. And which sits in an exact sequence as expected. So this projects onto the omega 1, well, over Z over QP. It doesn't make a difference. And the kernel of this is, in fact, a Tate twist by 1 of R tilde. So there is a way to make sense of this Tate twist here. So, yeah. Sorry, yes, that's part of the omega, yeah. So that's omega 1 of R over Z. That's your usual omega 1. That's omega 1 of R over F1, which doesn't make sense, so I put it in quotation marks. And this is omega 1 of Z over F1 tensored with R. No assumption. Yes. So it somehow gives you a sheaf on. So whenever you have such a diagram that somehow you pass to a perfectoid cover, then over this perfectoid cover you can make sense of this omega 1 over the field with one element. But somehow you can't do this over the base, which you can already see because you have a Tate twist here, and some of this Tate twist doesn't really make sense if you didn't pass to some large cover. P is invertible in the sequence, yes. I'm over QP. Okay. And then there's the third phase of perfectoid spaces. And so this phase started March 22nd, 2011. So what happened there was that there was some conference in Princeton where at 14:30 I gave a talk on perfectoid spaces, which was essentially the first big talk about them. And then just the talk after that, 16, Jared Weinstein gave equations for the Lubin-Tate tower at infinite level. So what he did there was he considered some huge algebra and divided out some element called delta. And well, from this description, it was obvious that what he was describing there was a perfectoid space. And so at this point, it became clear that there are, in fact, other natural examples of perfectoid spaces. So let me recall just very briefly what the Lewin-Tate tower is. So Jared will give 2 talks about this. So it's a tower which starts with M0, which is an n-1 dimensional open unit ball. And then over it you have some tower where Mn over M0 is some GLN. Oh, sorry. I shouldn't put 2 n's here. Mk is some GLN of Z mod p to the k torsor. So this is a universal deformation space of a formal group of dimension 1 and height n. And on the generic fiber, you can trivialize its Tate module in any finite stage of the Tate module. And you get some finite étale cover of the base space. And so some of the whole picture should be a GLN ZP torsor. And for a reason that I will explain in a second, people wanted to make sense of the inverse limit of this tower. Unfortunately, you lose all finiteness statements as you go up this tower. So you run into some highly non-Euclidean rings as you do this. And so there was no notion of rigid analytic space, which this could be. So people got around this, so Faltings and Fark, by considering specific integral models for all spaces involved and then taking the inverse limit in the category of formal schemes. But in some sense, that's not really what you want to do, because this choice of formal models is somewhat arbitrary, and so as you go to more complicated spaces, it gets more and more complicated to construct these integral models. So in this Lewin-Tate case, there are some very nice integral models, but I mean Greenfeld's ones, but I mean even they in this case are not the correct ones to consider, because you need some p-adic formal schemes. But what Jared proved is that the inverse limit of these guys exists as a perfectoid space. And so, I mean, this fact in itself turned out to be very useful for Jared, because he was trying to do computations on the space, and before that he had to tiptoe around with just all these finite level guys, but it's actually much more convenient to work at infinite level. So for example, you can give explicit descriptions of all the group actions on this ring, whereas you can't give the similar descriptions at finite level. So in some sense, this infinite level guy is much simpler than all the individual finite level ones. And so let me briefly explain why one would want to consider, one reason that one might want to consider these guys at infinite level. So the story is that there is a second tower of rigid analytic varieties which looks a bit similar. So here you start with something called Greenfeld's upper half space. So it's you take the projective space and you remove the union of all rational hyperplanes. So QP rational. Then over it you have, again, such a tower, which this time forms a cover for the group of units in a division algebra. And then again, this guy is a perfectoid space. And there is this famous theorem of faultings that at infinite level, the Lubin-Tate tower and the Drinfeld tower become isomorphic. But one very hard part was already to make precise what he meant by that, because there was no framework where both of these objects existed. And so this was worked out more carefully by Fark. And somehow as this isomorphism of perfectoid spaces, it was proved in my joint paper with Jared. It's the same n as the n minus 1 dimensional ball there.
Oh, okay.
And it's GLN, ZP, etc. Is it? So some of what this means is that there are actually very natural examples that you would want to consider. And in this business, they're mostly just there as a framework for some infinite type rigid geometry. And I should say that for some very special, because it's certainly not true that for any kind of infinite type thing, you would get something reasonable, but somehow all these towers that occur in nature, they seem to have this property that as you go up the tower, you join more and more p-power roots in some sense. Also, I should stress again that at least as far as I'm aware, it's not a good idea to tilt these guys. Tilt. I mean, you can just tilt them and get some eco-characteristic perfectoid space, but I don't think it's of use. But I mean, I might be wrong. But and there are some other examples of some of the same phenomenon. So one are Shimura varieties at infinite level that we will hear about on Friday. So can take the inverse limit over all levels at P of a Shimura variety for some fixed tame level away from P. And I mean, that's very closely related to this business of completed cohomology that Emerton introduced. And it allows you to prove some results about completed cohomology. And also coming back to abelian varieties or elliptic curves, you can again take some abelian variety A, and then previously I fixed the lifter for Frobenius, but you can also just take the multiplication by P maps as transition maps. And then again the inverse limit will be perfectoid. And I don't know, maybe there are more examples. I don't know. But these are the examples that I'm aware of. And I think that's what I want to say about as the overview.